Hello, I'm Yasser Ashraf Gandomi, postdoctoral associate at Brachet Lab from the Massachusetts Institute of Technology, and today I will be talking about lithium-conducting composite polymer-ceramic membranes for non-aqueous redox flow batteries. This work is a collaborative work between MIT and Caltech at Russia. To reduce the carbon footprint from carbon-intensive energy sources like fossil fuels, we need to incorporate renewable energy sources. And to fully integrate renewable energy sources within the electric grid, we need high performance and reliable energy storage technologies. Pumped hydro, compressed air, flywheel, and different type of batteries, conventional flow batteries are some of the examples. More than 95% of the installed capacity are the pumped hydro. You see an example on the bottom left corner installed in Michigan. Among these technologies, we are interested in electrochemical-based systems, including enclosed, hybrid metal flow batteries, and conventional flow batteries. I'm showing you here a conventional flow battery where we store the energy externally to the reactor within the low potential and high potential electrolytes that can include organic or inorganic active materials, supporting electrolytes and solvent. And when we run the cell, state of charge of the battery comes down, then we flip the polarities and start charging. This process can happen actually indefinitely as long as our electrolytes or reactors doesn't degrade. And then the reactors includes different components that flow plates, flow fields, membranes, and the electrodes are some of the major components. Membranes, as the heart of the reactor, must provide ionic pathway for shuttling ions. Shuttling ions are responsible for maintaining electron neutrality throughout the reactor. And also they must prevent crossover of electroactive species, because otherwise, as a result of crossover, we might have reversible or irreversible capacity decay. Flow plates can have different designs, are responsible for distributing electrolytes across the electrodes. And we usually use high surface area porous electrodes for providing active area for the reactions to take place. Decoupled energy and power scaling, location independence are the major attributes of redox flow batteries. Also, simple manufacturing and high durability and low maintenance make them a very suitable candidates for energy intensive grid storage applications. For this talk, I will be focusing on the membranes. Different membrane types have been developed for redox flow batteries. On-exchange membranes are some of the most popular ones in terms of organic or inorganic polymers. They are fixed, they include a fixed charge within their structures that can be negatively or positively charged. They attract counterions and repels the coions. They operate based on the principle of charge exclusion, and fluorinated membranes, Nafion would be the most important example of this family, have been successfully used for all vanadium redox flow batteries. The other categories are the porous separators that they operate based on size exclusion. They're very interesting and very promising to be used for large size organic materials like redox active ligamers or redox active colloids or redox active polymers. And they must provide ionic pathway for charge balancing ion. And the third category is the single ion conductors, and which is the focus of my talk today. NASICON-type ceramic electrolytes as the single ion conductors have been used successfully for solid-state batteries. NASICON stands for sodium superionic conductors, can have the generic form as I'm showing on the top left corner of this slide. And also I'm showing you 2.2 unit cell, including sodium, zirconium, silicon, and oxygen, phosphor, where the red dots are the oxygen, the purple the sodium, light green zirconium, and dark green sites shared by silicon and the phosphor. Exceptional and ultra high durability, along with high conductivity in the order of millisiemens per centimeter, are the major properties of NASICON-type electrolytes. For the application of non-aqueous redox flow batteries, we are interested in composite polymer ceramics to tune the mechanical and electrochemical performance. We have used PVDF as the polymeric matrix. PVDF has been widely used for lithium solid-state batteries. And also we are using lithium perchlorate as the salt for increasing the ionic conductivity, and NASICON-type LATP structure, including lithium, aluminum, titanium, and phosphor and oxygen. 30.4% for the salt, and also 44% for the ceramic is what we have used for synthesizing the ceramic structures, the composite ceramic structures. To prepare the ceramic pellets, lithium carbonate, titanium oxide, ammonium dihydrogen phosphate, along with aluminum oxide. After mixing and milling and adding burnable separator and undergoing the first annealing step at 750, we prepared the ceramic state material. Then we took those ceramic state material and add 3% PEG and acetone. And after compressing and second step annealing at 850, we could prepare final ceramic pellets. Looking under the SEM, average grain size was about 1 micrometer with a density of 80 to 90%. And analyzing the EDX data, we could confirm the elemental composition of the LATP structure, including oxygen, aluminum, phosphor, and titanium. To prepare the composite ceramic membranes, we took the PVDF powders and add the solvent DMF, and we prepared viscous polymer solution, and then we add lithium perchlorate and LATP. After continuous stirring at 1400 RPM, we prepared tape casting solution. Using tape casting solution within the Dr. blade apparatus, we can prepare the sym films, and then we dry them within the oven to prepare dense solid membranes. They have a solid white color, and we could tune the thickness between 40 to 100 microns. The first step was to look at their stability within the coin cells in the solid state. These experiments have been done in Caltech, sandwich the composite membranes between lithium anode and the cathode. We looked at their stability at 60 degrees C and also room temperature for extended days. As you can see here, they maintained their stability throughout the entire experiment, which was very encouraging. The next step was to look at their performance within the flow cell architecture. For the flow cell experiments, we also prepared LATP, also NASICON-type structures. This also had germanium in addition to the major components used for LATP. So I ran these composite membranes within the flow cell architecture using LATFSI and acetonitrile, and we could achieve 2.13 Siemens per centimeter with LATP and 1.62 millisiemens per centimeter with LAGTP. These values are pretty comparable with the state-of-the-art NASICON-type membranes reported from San Diego National Lab. So we also wanted to make sure that the performance of these membranes are superior within the flow cell architecture. This is the miniature flow cell we have designed and built in-house in our lab. So we use composite ceramic membranes within this structure using porous electrodes and flow field. And the top right, you see assembled version of our miniature flow fields. And I also use this flow field within a single electrolyte apparatus using Tempo and Tempo Plus as the electroactive species and LATFSI and different solvents. I use single electrolyte structures to maintain a constant state of charge throughout the experiments. So the first data I'm showing you is a polarization analysis. I ran the battery from 0 to 0.4 volt. I recorded the performance or the current density as the outcome of the battery. As you can see here, we could achieve up to 85 milliamp centimeter square at 0.4 volt as the overpotential with the acetonitrile and about 10 milliamp centimeter square with the propylene carbonate, and almost linear trend confirming almost negligible mass transport overpotential. The next step was to analyze the performance with other ceramic structures. We ran the similar experiments with acetonitrile and PC, and comparing them side by side, it's very clear that the ceramic structures contribute to the performance when we use highly conductive solvents like acetonitrile. But when we use PC, the ceramic structure does not contribute to the improved performance. And regardless of the structures, we could achieve almost 5 times higher performance with acetonitrile compared to the propylene carbonate. It was also important to make sure that the stability of these membranes are maintained. So what I'm showing here is the SEM images of the composite membranes when we took before soaking them in a solution containing acetonitrile. On the right, you see the SEM images after the soak. It's very clear that after the soak, we see wide, large voids within the structure. And comparing the elemental composition before and after, it's clear that we have lost Cl, O, and F after soaking. Almost more than 10% of the mass was lost. And it's mostly the the salt or lithium perchlorate. So the salt is being rejected after we soak these membranes within the acetyl nitrile. So it was necessary for us to reassess our synthesis and prepare membranes without the salt. So here I'm showing you 3 different configurations of the membranes we synthesized, LATP and PVDF only, and then 2 different configurations with ceramic and salt and with salt only. And we ran these experiments with PC and acetonitrile. It's very clear that when we do not use salt within the structure, the performance is compromised. However, if we look at this performance with LATP and PVDF only, we can achieve up to 40 milliamp per centimeter square with acetonitrile and about 5 milliamp per centimeter square with the propylene carbonate. Therefore, they are promising membranes to be used for long duration cycling if our purpose is not to achieve high performance. And the last step was to make sure that the mechanical stability are maintained. So we did similar experiments. We soaked these composite membranes in the solution containing different solvents and also tempo. And as you can see here, the loss in the mass was negligible after a long duration soaking. And also I ran a long duration electrochemical impedance spectroscopy analysis when I recorded the high frequency resistance throughout different days and more than 14 days. And as you can see here, almost negligible increase in HFR was recorded, confirming a good mechanical and electrochemical stability. So the major conclusion, you could successfully use lithium conducting composite polymer-ceramic structures for non-aqueous redox flow batteries. And they were stable chemically and electrochemically, even when the radical organics were used like tempo. The addition of salt improved the performance significantly, but the final structure was unstable. We showed that ceramic microstructure is important when we are using highly conductive solvents. And these PVDF-based composite membranes are pretty promising to be used for long duration cycling. At the end, I would like to thank my colleagues and friends at Professor Brashett's lab at MIT and my funding source at J. Caesar. I would like to thank you for your attention. Please feel free to email me any questions you might have at ygandomi@mit.edu. I hope you stay healthy and well.